inhibitory mechanism. And so what we have is, if we have very high VEGF levels, all these endothelial cells, they will basically express very high levels of delta-like ligand 4, and as a result of that, they will all inhibit their neighbors. And so in the end, you get a system where everything gets inhibited and nothing is moving anymore. And so this, well, whether this is actually a mechanism that is happening in reality, well, we don't know. There may be also other mechanisms, maybe, but at least this model suggests that it could be a mechanism. Why in high VEGF concentrations actually, very high VEGF concentrations, the vasculature is actually not recovered, leading to a delayed or even a non-union. I don't know, I'm not really looking at the time, so we should, okay. 5, 10 minutes. 5, okay. So this was actually, let's say, the first multi-scale model that we had, already accounting for some effects of oxygen, but obviously there are much more effects. I mean, we only added some terms that accounted for angiogenesis and osteogenesis, but so what we're currently doing, and this is actually ongoing work, is add even more terms or make even more terms oxygen dependent. And so what we're currently doing is also introduce depth terms, because of course if oxygen levels drop between critical levels, cells will die in the end. And so we do that for all cell types, but it's really a matter, of course, in trying to guess what is a good threshold. And for that, it comes down to going in the literature and trying to estimate these numbers. So these expression levels are already depending on oxygen, but also basically all the differentiation steps are also made dependent on oxygen, because again, this is known from literature that, for instance, chondrocyte differentiation is actually more optimal at fairly low oxygen concentrations, while osteoblast differentiation is actually optimal or more optimal at fairly high oxygen concentrations. And so we're also adding oxygen consumption rates for different cell types, and so on and so on. And so what can we do now? Well, what we could do actually with this enhanced model is see actually what happens in the case of a very large bone defect, which is problematic. I mean, clinicians have problems with that in healing these. And obviously that's why we need tissue engineering. And so what we did, we also simulated such a large bone defect. Now, obviously, I'm sorry, but it's not really that visible, but what we do actually is we just extend our domain. So we just make a much larger domain. And so what we see is that actually at some point in these large defects, the vessel just stops. Now, why is this? Simply because they do not receive any angiogenic signal anymore. And why is that? Because there are no cells anymore to actually express VEGF. And why is that? Because the oxygen level is just way too low and they die. So there are no living cells anymore, even not chondrocytes, although they are supposed to be able to cope with quite low levels of oxygen. But it just takes too long for the vessels to arrive. And so in the end, by the time they would be able to arrive, everything is dead. You can actually also look at, for instance, the bone response that we predict in these cases. And so interestingly, what we see is a kind of bony cap that is being formed around these bony ends. And so again, this makes sense because bone doesn't like hypoxic environments. And since there are no vessels here, it just stops here. And interestingly, this is also something that you find in experimental situations. Some more, let's say, interesting results. We find actually some kind of tree-like vascular structures at the front of our vessel front. And we find them in our model, but also in the experiments. Now we don't have a full explanation why this is going on here, but it was interesting to see that we come up with structures that well, are kind of similar to what we see in the experiments. So this is just a preliminary conclusion, because like I said, this is ongoing work. So but what we see actually is that a tiny arrival of vessels is really key to healing these large bone defects. Because like I said, if it just takes too long for the vessels to arrive, all the chondrocytes are dead and they cannot express any VHF anymore. And so obviously it also means that the migration speed of the endothelial cells is a crucial parameter. So that's basically the story I wanted to tell. So just a few concluding remarks. I mean, maybe the most important one is we have this model now, but of course it needs much more validation, and that's also what we're currently doing. For instance, try to see actually whether what we predict for this large bone defect, whether this is actually also happening in reality. One also interesting remark, certainly for this workshop, which is supposed to be focused on flow, we don't have any blood flow yet, and this is obviously also important. Alright, so some acknowledgements. I mean, this is actually the person who did all the work. It's a PhD student of mine who I'm co-supervising with these series. Like I said, also the coupling with experiments is really key, and so that's why we actually need these people here to do the experiments. Finally, also some announcements. Some very interesting conferences where you definitely should go, especially if you're interested in biomechanics. There is the ESB 2013 organized in Patra by Janis Misilis, and there is ICCB 2013 organized by me and a colleague in Leuven. Abstract submission deadline 31st of January, so you still have some time to come up with a good abstract. Thanks.
Thank you. Hans, questions?
Hans, when we were doing the experiments for the healing of bones, not in non-unions, but let's say for normal, let's say, healing, we observed that up to the second week, the end of the second week, all the characteristics of the bone were going down. And then we had, the creation of the new bone. Is there any way to predict that from that model?
Not in this model, because actually there is no mechanics in this model.
It's not mechanics, it's an observation.
It's a mechanical, you mean the mechanical properties, so the stiffness is decreasing.
Yeah.
I assume this has to do with osteoclastic activity also, so you will have resorption of tissue, which is not included in this model, but you could do it, because you could add an additional variable accounting for osteoclast densities, for instance.
Oh, yeah.
But it's not included yet. In fact, the whole remodeling, bone remodeling, and actually also vascular remodeling is not in this model. It actually focuses much more indeed on this androgenic sprouting and how this could affect bone regeneration.
Okay, thank you.
What is the let's say sequence of chemical events that you resorb a piece of cartilage and then build a piece of bone? What are the cells and growth factors, whatever, involved? Probably I didn't get the details, but you showed a simulation where you said, okay, and here I have first cartilage and then bone. How can one imagine this?
Yeah. I mean, the crucial process that takes place there is chondrocyte hypertrophy. And it basically means that your chondrocyte will get terminally differentiated. I mean, morphologically, it's just growing in size, but what is very important is that it will initiate vascularization because it starts expressing VHF, and it will also initiate osteogenesis. And it's a very complex process that we're actually not quite capturing here in detail, because we do it, let's say, in a more phenomenological way. We don't add variables to account for chondrocyte differentiation. What we do is we say that if the cartilage matrix density reaches a certain level, it actually favors the replacement of chondrocytes by osteoblasts. But in reality, it's not really a replacement, because the chondrocytes just die and they make space for blood vessels, and with the blood vessels actually the
There
osteoblasts.
comes a whole formation process afterwards. But
Sorry?
I'm wondering where the extracellular cartilage tissue is gone.
But it gets mineralized.
Are you really building it on the cartilage? Are you building the
No,
bone on the cartilage?
the
Because
cartilage-
that's a delicate thing where the
Yeah.
neurologist say, okay, bone is not cartilage, right?
The
So
car-
how
yeah.
do you transport it off and then get it bone?
The
You
car-
have the cartilage, I'm sorry.
So
yeah, yeah.
You have the cartilage skeleton, skeleton. It's like matrix on which you build the bone. It's endochondral and endomembrane
Endochondral
ossification.
yeah.
So basically, you need to have first the cartilage, and then on that you build.
So you
on
build
the bone.
within the cartilage, organic material, you build the minerals in there. You have any additional collagen.
I must say I don't know the details about how this mineralization takes place, but I understood it's actually the hypertrophic chondrocytes who are initiating the mineralization. But
But not the position, right? Because
Sorry?
osteoblasts they do
no,
always both.
indeed,
They
but
both
because
become
this comes
mineralized.
with the blood vessels, and the blood vessels actually with the blood vessels actually the bone precursors come,
Yeah.
and they will actually lay down new bone.
And
And
they
then this-
also new organic material, right? But I'm
Right.
wondering what is now the interface between the old cartilage material, the new organic bone material, and the mineral? It's just a question.
You mean how it looks morphologically?
Yes,
or-
absolutely, because
Yeah.
it's a big difference.
Okay.
First, it's like a cartilage. It gets mineralized. This cartilage, collagenous,
Yes.
plus these other gags and all. Then it gets mineralized as the osteoblasts arrive. So basically, osteoblasts start mineralizing the whole structure. So they're building up on the already existing
Right.
cartilage.
So they are mineralizing the cartilage,
Yeah.
basically.
Yes.
Well,
And
they're
then
depositing
they do
collagen.
would be bone. So then they eat up the osteoblasts and then it's really
They
bone.
die. The
It makes-
hypertrophic chondrocytes
Yeah,
die.
yeah. And there
Yeah.
makes
And
space
the
also
next
that way.
remodeling cycle is really bone. So
Exactly, because this all need to be remodeled by osteoclast by
And then they remodel it and then they
BMUs.
build the remodeling.
Osteoclasts also, they are
Yeah.
constantly remodeling.
So there's an intermediate mineralized cartilage state.
yeah, it's mineralized
So that is
cartilage.
correct.
It's mineralized cartilage. Yeah.
Yes and no. I mean, the blood vessels coming inside, they're dissolving, they're producing a lot of matrix metal proteinase, a lot of enzymes, and they're dissolved with the cartilage, just going like that, going inside, penetrating in the cartilage, is disappearing, blood vessels are coming, and the osteoblasts are coming, start.
Yeah, but this was my what I would have imagined, that they
Yeah.
dissolve
Exactly. It's
the old
like-
cartilage and they build real bone,
Exactly.
and they don't take an old cartilage with a
No,
dead
they
cell.
should be dissolved by different enzymes.
So we have 2 minutes.
Okay, very interesting. More questions? Okay, so we can continue discussion. So now we have lunch. Thanks again, friends, for the we have a break 1 hour for the lunch outside
Yes, I would have.
the room.